Hi everyone, my name is Yebo Feng, a PhD student from University of Oregon. Today I'm going to talk about our paper toward explainable and adaptable detection and classification of distributed denial of service attack. Another cause of this paper is my advisor, Jun Lee. So let's start. So first of all, let's talk about the distributed denial of service attack, aka DDoS attack. So DDoS attacks, by attacking the bandwidth or resources of the victim on the internet from multiple compromised systems, it disturbs the service of the victim and make it unavailable to its legitimate users. Just as the figure shown on the slide, the DDoS attacker usually will compromise a lot of computers to form a very massive botnet and control the botnet to send malicious requests or packets to the victim system to overwhelm the victim. So to prevent and mitigate such attack, we need to have a very accurate and fast DDoS detection and classification system, which is also the purpose of this paper. The detection and classification of DDoS attacks is not a new topic. Decades of research and industry efforts have led to a myriad of DDoS detection and classification approaches. Nowadays, many researchers began to utilize machine learning techniques in detecting and classifying DDoS attacks. However, such methods have two negative aspects. First of all, the prediction results are inexplicable. An unexplainable result may lead to unexpected collateral damage when conducting access control. This is due to the nature of some popular machine learning techniques like neural network, deep learning, or MLP. Secondly, the learning-based methods are not adaptive because a model trained in one environment cannot easily apply to another environment unless you retrain the model with updated data. So in this paper, we propose a learning-based DDoS traffic detection and classification method. It utilizes a modified k-nearest neighbors algorithm to detect DDoS threats. It then conducts fine-grained traffic classification using risk degree sorting with grads. To improve the efficiency, we use a k-dimensional tree to partition the searching space of KNN, reducing the time for queries significantly. Compared with the previous learning-based DDoS detection and classification approaches, our approach is highly explainable and adaptive. Our approach has two phases, which are DDoS detection phase and the classification phase. The figure on the right is the operational model of our approach. It monitors the traffic in batches, and each batch T is a uniform time bin. And in our implementation, we use 5 seconds as a batch. During each batch, our approach extracts features to form a traffic profile and input the traffic profile into the detection module. And once the detection module detects some DDoS threats, it will enter the classification phase. Our approach will also generate the traffic profile for each source IP and determine whether the source IP is malicious or not according to the features. Our approach is compatible with some very popular traffic capture engines like NetFlow or SFlow. Now let's talk about the detection of DDoS traffic. We use k-nearest neighbors algorithm in the detection of DDoS traffic because KNN is a highly explainable machine learning algorithm. Although it is simple, but it is straightforward and very stable in dealing with low-dimensional data. Although KNN takes no time to train the model, but the prediction requires a time complexity of O n log n to complete. It is very expensive, especially you deploy this method in an SP level network. Therefore, we leverage the KD tree to partition the searching space of KNN reducing the number of data points to enumerate. Furthermore, our approach generates a decision tree-like the structure out of the KD tree, which can reduce the time complexity for traffic monitoring to nearly OD, where D is the depth of the tree. These figures clearly show how our method works. First of all, we use KD tree partition to cut the searching space into different sub-areas. Unlike other KD tree-based KN algorithms, we will do one step further. We will scan all the sub-areas. If one type of the training data dominates this area, we mark this area as a confirmed area, such as areas with red and green colors in the figure. If one prediction sample appears in the confirmed area, we directly label its identity as the identity of the confirmed areas without conducting any KN searching. We only conduct the KN searching when the prediction samples appear in the unconfirmed area, such as the area with blue colors in the figure. So once DDoS threat is detected in the DDoS detection phase, our approach will enter the DDoS classification phase. The design philosophy of our approach is the traffic profile is currently in a very malicious position, and we need to conduct the access control on some of the IP sources so that the traffic profile can return to a benign area, just as the sample shown in the figure. The current traffic profile is in a benign area, is in a malicious area, and we need to calculate the shortest distance from the current position to a confirmed benign area. We conduct the classification for malicious source by building the traffic profiles for each IP addresses. Then we mark IPs as malicious in a particular order, and this order is according to the detection result. We will build a risk degree score for each IP source, and we mark those malicious IPs one by one until the overall traffic profile returns to a benign area. And during this procedure, we also need to minimize the impact to other features of the overall traffic profile, so that we can minimize the collateral damage to the legitimate users. We consider this as an optimization problem with two constraints. First of all, we need to make sure in the very end, the overall traffic profile return to a benign area. And we also need to make sure the impact to other legitimate users is minimal. And we want to get an IP set so that it's qualified to all these constraints. Deriving the optimal solution of this optimization problem is very expensive. So in order to conduct the classification in real time on an ISP level network, we use grad partition on the searching space of the IP profile to accelerate the IP classification. It can derive a near optimal solution in real time. Just as the figure shows, we first partition the searching space of the IP profiles into grads. Then we select the malicious IPs one by one according to the risk degree scores. Then we can derive an IP set of the malicious IPs that needs access control. Now let's move to the adaptability of our approach. Users do not need to retrain the proposed model to fit it into a different network environment. They can easily use some prior knowledge to refit the model. So if we have the traffic measurement information about the new environment, we can simply normalize the KN searching space from the trained environment to the new environment according to two networks traffic distribution. And also, if luckily the user have some like sample data or labeled data from the new environment, we can efficiently conduct online learning with KN searching space because KN does not require retraining of the model. In some circumstances, the users of this method may already have some incomplete thread values or rules in the new network environment. They can also build a decision tree like the structure on the preliminary result and merge it with the trend classifier. To evaluate our work, we trained our method with 4 public DDoS datasets, including Drupal 2009, Kata 2007. We compared our approach with FastNetMo, a commercial level DDoS detection software. Just as the figure on the left shows, our approach can mitigate more DDoS traffic compared with FastNetMo. We also transfer our approach to a different environment with just some network measurement data, which is an ISP level traffic link. It can detect and classify DDoS traffic with a delay of around 5 seconds in the ISP environment. So thank you for your listening to this presentation. And we also want to thank the US Department of Homeland Security to fund this project. Just feel free to ask any questions if you want.